Welcome to This Explainer. Today, we are taking a journey that is going to completely change how you look at a spinning piece of machinery. We're going to stop treating bearings like cheap, throwaway commodities and start understanding them for what they truly are: highly engineered, absolute mission-critical elements. Think about it. Every mechanical system out there, from a towering wind turbine to your electric motor, all the way down to a complex package sorting conveyor, is literally only as reliable as the bearings inside it.
You know, there is a classic rookie mistake we see all the time in engineering. Too many designers just figure out the shaft diameter, open up a catalog like McMaster Carr, filter by the bore size, pick the cheapest one that fits, and boom, move on. And what happens next? Well, sure, the prototype might spin perfectly in the lab, but choosing the wrong bearing is a ticking time bomb. It eventually leads to excessive vibration, intense heat, shaft wobble, and premature failure out in the field. It's exactly the difference between a rock-solid design and a total warranty nightmare. So before we get into all the complex variations, let's just ground ourselves for a second. What actually is a bearing? At its core, it's a machine element that constrains motion in undesired directions while allowing it in the desired one. It transfers the load between the moving and stationary parts. Without them, every single rotating shaft you've ever seen would just grind directly against its housing, generate massive amounts of friction, and the whole system would just completely seize up. All right, here is our roadmap for today. We're going to cover mastering core forces, the ball bearing family, the roller bearing family, plane and fluid dynamics, specialty designs, and wrap up with the ultimate selection sequence. Starting right off with Section 1, Mastering Core Forces. Believe it or not, the physical chaos inside any machine basically boils down to two things. Most bearings fall into groups based entirely on their ability to handle two very specific loads. First, you have radial loads. These are forces applied perpendicular to the shaft, so think of the weight of a super heavy spinning gear pushing straight down. Then you have axial loads, which we also call thrust loads. These are forces applied parallel to the shaft, kind of like the forward push of a boat propeller. Every bearing is designed to handle one, the other, or a very specific mathematical combination of the two. Moving on to Section 2, the ball bearing family. So this family uses point contact to reduce friction at incredibly high speeds. The most common one you'll see is the deep groove ball bearing. They're literally in everything, from electric motors to skateboard wheels. They are fantastic for high speed and radial loads, but man, they handle misalignment terribly. And watch out, because uncontrolled axial float here causes fretting and highly unpredictable behavior. Just look at the bearing life equation, specifically that exponent of 3. That means bearing life drops off a cliff as the load increases. Next up, we have the angular contact bearing. These use offset raceways, usually 15, 25, or 40 degrees, to handle combined radial and axial loads. But because of their geometry, they generate a reaction force. That means they absolutely must be mounted in pairs, back-to-back or face-to-face. That's standard practice in precision stuff like CNC spindles. 3 degrees doesn't sound like much, right? But that is the absolute maximum angular misalignment that a self-aligning ball bearing can handle, all thanks to its spherical outer raceway. If you're designing agricultural equipment or, say, a really long conveyor system where you just know the shaft is going to bend and deflect under heavy loads, this is your best friend. But there is a massive catch. If you have significant axial thrust loads, this bearing is terrible. It will completely fail. Now, that brings us to the thrust ball bearing. These are flat, washer-style bearings designed to take purely axial force. They are amazing for lazy Susan turntables or heavy bar stool swivels. But here is the absolute kicker. If you apply any radial force to a thrust bearing, the balls will literally slide instead of roll, and it'll destroy itself in no time. Plus, under really low loads, they actually require continuous lubrication just to prevent the internal cage from skidding. All right, Section 3. The roller bearing family. Here's where things get heavy-duty. By swapping a spherical ball out for a cylindrical roller, we fundamentally changed from point contact to line contact. This physical switch gives you a massive 1.5 to 3 times increase in load capacity for the exact same amount of space. But physics always demands a sacrifice, right? In this case, you lose speed capability and you lose tolerance for misalignment because of the increased friction along that longer line of contact. We've got some real heavy hitters in this family. Cylindrical roller bearings are optimized for high radial loads and speeds, super common in train traction motors. And what's really amazing is the NU-type configuration. It intentionally has separated rings that let the shaft float axially. This brilliantly accommodates thermal shaft growth when a gearbox heats up.
Then you've got spherical roller bearings. These things survive conditions that would rapidly destroy more delicate designs. They handle enormous radial loads while taking up to 2.5 degrees of misalignment, making them the absolute go-to for massive applications, like wind turbine main shafts and ship propellers. Then there's the tapered roller bearing, heavily used in automotive wheel hubs and helicopter gearboxes because they handle combined loads incredibly effectively. But getting the preload right is literally a make or break situation. If your preload is too low, the rollers skew in the raceway, causing rapid wear and that classic, terrible bearing rumble noise. But if it's too tight, you generate excessive heat that quite literally cooks and destroys the lubricant. Precision here is totally non-negotiable. And speaking of non-negotiables, the number 58. This relates to needle roller bearings, which have a really thin 3-to-1 length-to-diameter ratio just to save space. When the shaft itself acts as the inner race, that shaft must possess a minimum of 58 Rockwell hardness, along with a super smooth 0.4 micrometer finish. If your shaft is softer than 58 Rockwell, those little needles will press right into the steel, causing immediate, permanent indentation and basically a rapid spiral toward failure. Shifting gears a bit, Section 4, Plane and Fluid Dynamics. Let's ditch the rolling elements entirely for a second. Plane bearings, which are often called bushings, use a lubricant film or a self-lubricating liner. They are actually far superior for low-speed or heavy oscillating motion. Think engine wrist pins or the massive pivot joints on an airplane's landing gear. Fluid bearings, on the other hand, replace solid contact entirely with a pressurized fluid film. In high-speed hard drives or giant steam turbines, fluid bearings offer near-zero friction at operating speed. But because friction is so high at startup, they often need an external hydrostatic lift pump just to get spinning safely without damaging themselves. Okay, on to Section 5, Specialty Bearing Designs. Let's do a really quick tour of the weird and wonderful. Magnetic bearings use electromagnetic force to suspend the shaft. Zero contact, zero wear, zero lubrication, absolutely perfect for clean rooms like semiconductor fabs. The severe trade-off, though, if the power fails, the magnetic field dies and that shaft drops immediately. Then you have flexure bearings, which utilize elastic deflection for zero-wear motion over a limited arc, heavily used in tiny medical equipment. And linear bearings, well, they take the recirculating ball principle and just lay it out flat for high-precision CNC machine axes. Okay, I literally couldn't leave this out. Jewel bearings. Yes, they use actual synthetic ruby or sapphire as the bearing surface. If you've ever looked inside a really high-end mechanical watch, you'll see these. The pivot shafts in there are less than 0.5 millimeter in diameter. At that microscopic scale, standard oil would eventually migrate away or literally create more drag than it prevents. Synthetic sapphire completely solves this tiny scale friction issue without needing standard oil at all. It's brilliant. Finally, Section 6, the ultimate selection sequence. This is it, the master formula. Please don't just open a catalog and pick a size. Step 1, note the load direction. Is it radial, is it axial, or is it both? Step 2, determine the operating speed. Step 3, assess the expected shaft deflection and misalignment. Just following this exact 3-step sequence before you ever even look at dimensions will put your bearing choices ahead of 90% of what gets designed in a hurry. So here's my question for you. Next time you look at a spinning shaft, whether it's on a bicycle, a wind turbine, or some massive industrial gear, will you just see a cheap catalog part, or will you see a highly engineered, precisely selected solution constantly fighting off physical chaos? Hopefully, this explainer gave you a whole new appreciation for the hidden mechanical world holding our modern lives together. Keep learning, keep asking questions, and I'll catch you in the next one.